We are the haptic interfaces for real-world objects team. We're composed of Courtney, Derek, Kevin, Andrew, Emmy, Tim, and myself, Sasha, and we're advised by Dr. Mark Miner. Some background for the project that we did is Dr. Mark Miner has a cyberhuman systems research team that for many years has been developing a cave virtual reality environment, and it utilizes multiple human senses to have a more realistic simulation. Currently, they have walls that project onto it to show the environment. There's a treadmill, a wind tunnel, and simulated rain. And the NSF gave a grant to Miner to make this a more realistic environment. The goal of this section of the project is to develop haptic interface robotic arms. This is a sense of feel that the user can interact with in the virtual reality environment, and they can feel the real world objects while they're in it. And the current goal is aimed at helping to rehabilitate patients with gait problems or Parkinson's disease.
Since the haptic arms being developed in the lab need end effectors, we are doing exactly that. The end effectors are basically handles taken from different objects, which include a cane, a walker, a wheelbarrow, a shopping cart, doorknob/handle, suitcase, a briefcase, and a box. Each one of the end effectors has a tool changer end, which connects to the robots, and a handle end, which is the one we're taking from the objects, so that the users can interact with the virtual objects inside the virtual world that the researchers are creating.
The design goals for this project include primarily to maximize rigidity. This is Dr. Miner's main concern because low rigidity could give his team problems when trying to develop control systems and maintain robot stability. Additionally, we want to make sure we accurately replicate the dynamics of every real-world object that we're simulating. We want to have a simple mounting scheme for our end effectors. We want to ensure that they are durable, compact enough to fit within the allotted space, have minimum weight, simple fabrication, and minimum cost. Additionally, our designs are required to be able to withstand a 25-pound design load at the intended loading point, which is approximately 12 inches from the load cell. Finally, we must ensure that our parts create a torque less than 25 pound-feet at the load cell to prevent damaging the robot or load cell.
So the main focus of our project was to design the interface between the robot load cell and the object end effectors. We wanted to keep the installation and swapping process of the end effectors as simple as possible for the users, so we went with the premise of a quick change tool changer. We had various designs for a possible tool changer, and ultimately we designed this mechanical twist lock tool changer that's shaped like an axe that you can see in the figure here. The left side of this figure is what's called the robot side of the tool changer. It's composed of 3 stacked plates that are permanently bolted onto the load cell of the robot. So you can see the top plate has an axe shape cutout, the middle plate is just a simple ring, and then the bottom plate holds the load cell bolt pattern. The right half of the tool changer is what's called the tool side, and that's what mounts to the different end effector objects. So on the back of this figure would be where the different end effector objects are bolted on. And then the axe shape on the front of the tool side here is what's able to slide into the axe cutout onto the top plate of the robot side and rotate 90 degrees. So because of the axe shape, a 90-degree rotation within the robot side of the tool changer prevents the whole tool side assembly from disengaging with the robot side. Finally, we use 2 vertical locking pins that aren't pictured here, but will be shown later to lock in the rotation of the axe tool changer and fix the end effector to the robot.
For the robot side of the tool changer, we decided to water jet stock that was the right thickness because of the more complex geometries and precise holes that we need on that side of the tool changer. On the tool side of the tool changer, we were having difficulties cutting the groove between the axe and the plate behind it safely, so we decided to split that into 2 separate components, with the axe being manufactured by CNC by the medical school machine shop, and then manufacturing by ourselves the plate behind that and the post that interfaces with the different handles. We primarily did this to save money and also because the posts change between each of the different objects. Below, we have pictures of a walker handle on our tool changer and also a wheelbarrow handle on the tool changer. We have a picture of the briefcase handle that we're going to be using. And then finally, we have a picture of the tool side of the tool changer without any handles attached to it.
To install the tool changer, the tool side is placed into the robot side and twisted 90 degrees clockwise. Then 2 ring pins are placed, and that holds together the entire tool changer and prevents rotation. We wanted this to be easy to install, and we have an average installation time of 9.8 seconds and an average uninstallation time of 1.7 seconds.
Here's a demonstration of our aluminum prototype being attached and removed. First, the tool side is inserted into the robot side. It's then turned 90 degrees clockwise, and the 2 retaining pins are inserted. To remove the tool changer, the 2 pins are simply removed, and the tool changer is twisted off and removed. Static load testing was done to verify that the manufactured prototypes would satisfy the design requirements as well as maximize their rigidity. This was done for both manufactured aluminum and for a 3D printed PLA set. They were both tested at a 1-inch lever arm with up to 75 pounds, and they had very similar displacements. The metal tool changer assembly displaced a maximum of 2.5 millimeters, and the PLA assembly displaced a maximum of 3 millimeters. The full walker assembly was tested as well, and at 70 pounds, it experienced a displacement of about 8 millimeters, most of which was due to elastic compliance in the walker itself. It was bending, whereas at the 25-pound design load, it only experienced a displacement of 2.5 millimeters. Our goal with this project was to create a set of end effectors which had a simple, efficient, and durable mounting scheme, which we felt we were able to accomplish. We would like to thank Dr. Miner and the Cyberhuman Systems team, as well as Dr. Tan and the University of Utah.